Hello everyone, welcome to our channel. And last time I built this. This is a 4-bit counter. Also, we have the touch switch, bonus table, multi-vibrator, and a tone generator. At the same time, an LED flasher. But now, we have a new toy module here. This is a toy module based on arthropod design, inspired by the arthropod. We have the two output LED, the power on LED. As you have seen here, it is the circuit is on. We have the transistor, a zener diode, resistors, a jumper settings for the output, and a jumper settings for the input. Also, we have this, a power header, input output power header, and lots of jumper wires. This is a collectible toy module. Once you have done the project, you can display it in your cabinet. It is capable of standing on its own, just like the other arthropod design toy module. So in this module, we're going to see how the constant current source functions. But this module is capable of making a constant voltage source. At the same time, it is also capable of being as a current source, constant current source. And also it is also function as a inverter or a buffer gate. So we have 4 functions in one module. As you have seen here, the transistor, power on LED, output LED, and now we can see how the module functions, our toy module. Let us see how it works. The circuit is on, powered by 5 volts. And now let us use this module as a constant voltage source by putting a jumper to the input. And then the other one, we are now using this as a constant voltage source. As you have seen here, our LED turns on, one LED. Now, the problem with the constant voltage source is when you connect another LED in series with the previous LED. Let us now connect the other LED in series by sliding a jumper. This is now what happened to a very small light with the blue and almost nothing with the LED red. You can see that when I see the lights of the LED red is almost nothing and the blue is very dim. That is the case of constant voltage source. Once you connect another LED in series with the other LED, the light is getting dimmer. So in order to to make a good circuit, or to make the LED to light both the LED, we're going to make a constant current source. So we're now going to use this module. We're setting the mode to constant current source. So let us now see. This is now the constant current source by sliding it again. And then this is the, when I connect the one LED in constant current source mode. As we have seen, still the same with the constant voltage source, LED turns on. And from the constant current source, if you connect excuse, another LED blue in series with the red LED, let us see what happens. Without changing voltage source, the same voltage source, 5 volts. Let us now connect. They are both lighting. Unlike the constant voltage source, when you connect the blue LED, the brightness of LED becomes dimmer, or almost nothing. While in constant current source, it gets its good lightings here. Did you see the light? So it means that constant current source is advisable to use and it applies to many different circuits because it is capable of supplying a constant current or source without changing the input voltage and without or any condition if the load is changing. If the load is changing, you can use the voltage of the load is changing, you can use a constant current source in order to provide a nice source or supply to the circuit. So let us see another function of this toy module. It also used as a buffer. Let us see. By using a arthropod design switch connected into the base. And no input, no output with input with output. Now it serves as a buffer gate using the switch. Okay, and now let us use this as an inverter by putting another switch, this arthropod design switch, into the base. And now let us connect again. So we're now going to use this as an inverter. So let us now check. No input with output. In the inverter, logic gates, with input, no output. Did you see? That is now functioning as an inverter logic gate. You can now put the module the toy module in your display cabinet as a souvenir after or once you've done the project. And this is displayable, collectible, and for keeps or as a souvenir items once you've done the project, or else your project will be wasted, or just you put that under your bed, or put that in your trash bin or in the box. So it's better to collect toy module aside from having a project as a souvenir, reminding that you already built a circuit. You once built the circuit. So let us now go to the how the circuit is working, or we can check the circuit diagram. This is the constant current source schematic diagram. We have the transistor in voltage divider configuration of transistor biasing, collector base emitter. I'm using 2N3904 with an output LED D1, that is the red one, and the blue one, connected by a header, jumper. We have this power on LED, the green one, and then the output, the blue in the red, and then the transistor 2N3904. This is the transistor located at the top, and RE. Also, we have the zener diode here, 2 zener diode, 1N4148, D4, D5, located at the tail of our module, the side, and the resistors at the tail of the toy module. And this is the input jumper header settings. If you're going to use a constant voltage source, you are using this portion, RB850 and RB2 1000 ohms connected to the header. Once you're going to use the constant current source, this portion, zener, with the 330 ohms resistor, you're just changing the settings of the jumper for the input. So this one is the arms, or the Gatling gun of the robot, and then this one are the input output power header. Located at the base. Oh, something wrong with the drawing. And then we have a jumper settings for the output LED. And this is the layout. We're going to use the layout. Let us now check how the circuit works I did not change. This should be now positive. Two positive. The same input. Only one negative, positive, negative input connected to the base of the transistor, and then the positive, and then the output connected to the collector. That is now our circuit diagram. If you are interested on how to design the circuit, we are now going to compute the values of the resistor and how the circuit derives, or how the constant voltage source and the constant current source is getting its design, or how the derivation. Let us now see how it works. First, we have this 5-volt supply, RB1, RB2, R1, power on LED, D1, and then RE. This is a transistor in voltage divider bias configuration. Since you know, in the module, I just changed the setting of the module to make it a constant voltage source using one LED. I just demonstrate that already. In this diagram, we are required to use this current 0.02 ampere for the LED to turn on. That is the given. All we need to do is to compute for the values of the resistor. That is the required current for the constant voltage source. This is the start of the design. 2N3904. And then you're going to choose the value of the voltage RE. The voltage in RE, 2 volts, and we're going to use this given. The voltage rating of the diode 1 is 1.8 volts. That is the red LED. The HFP transistor 100, the current 0.02, and then BE 0.07. All is in the data sheet of transistor and LED, and voltage drop at the RE is 2 volts. This is arbitrary values, BCC 5 volts. And now find R1, RB1, RB2, RE. So transistor in voltage divider configuration with red LED as a load. D2 is the power LED. And transistor in active mode. So we're going to use the transistor in active mode. So when you close the circuit, current flows into the R1 and powering the LED. That is the first KVL. BCC minus voltage drop, R1, D2. Now we have here transposition, substitution, calculation, 3.2 volts voltage drop across R1. Using Ohm's law to compute for R1, voltage VIR is equal to R1B over I, 3.2 volts. And then the current at the diode is in series with the resistor, the same. We get now 160 ohms, but I used 220 ohms available. So we get now the value of R1. And it is equal to 160 ohms, but I used 220 ohms, my available resistor. So, okay. Now let's go to the output side of the transistor. This is the output side. In here, the current of the load is the current of the LED, which is approximately equal to the current across emitter. That is the requirements of the design, because we're going to pass on the current here and transistor is in active mode. So in voltage divider configuration, this is the requirements. RB2 should be less than or equal to beta RE times 0.1. That is the required RB2 values. This is an equation 1. This is the requirements when you are going to bias the transistor in this voltage configuration, voltage divider. Excuse, beta is equal to HFE for Q1 biasing. Oh, okay, beta is equal to HFE. Now we have here, since we know that the voltage drop across the RE is 2 volts and the current is equal to the load or the diode current, because the resistor here, we're having a resistor here that act as a current limiter to the LED, aside from the constant current source. So here we have Ohm's law. Using Ohm's law, we know value of the voltage and the current. Now we have this 100 ohms. That is the value of RE, 100 ohms. Since we know the value of RE, we're now going to compute what is the base voltage here. The base voltage here is equal to voltage at base emitter plus the voltage at RE. Since we know the voltage at RE and the voltage at the base emitter, in case of silicon diode, that is 0.7 volts, the voltage at the base is equal to the voltage BE plus voltage RE, which is also equal to the voltage RB2, which is BE 0.7 volts plus voltage RE given 2 volts, that is arbitrary values, 2.7 volts. Voltage at the base is equal to voltage RB2, also equal to the voltage of the base BRB2 and BBE plus BRE. Now we know that the voltage is 2.7 volts. Let us now go to the input side. This is now the input side. We're going to use a KBL, BCC minus the voltage drop RB1, and since we know the voltage drop at RB2 is equal to 0. Kirchhoff's voltage law, transposition, substitution, since we know that the value 2.7 from our previous equation, we got voltage RB1 is 2.3 volts, so we now know the voltage drop across RB1. And then we are going to make a ratio and proportion in this voltage divider bias configuration. Taking the ratio of voltage drop at RB2 over RB1, 2.7, 2.3, we got 1.17, also equal to the ratio of the two resistors, since we are going to compute for the value of the resistor, 1.17. The ratio of voltage equal to the ratio of the resistor in voltage divider bias configuration. And using equation 1, RB2 should be equal or less than B beta RE times 0.1. Since we know the value of RE, which is 100, substitution, calculation 1000 ohms. RB2 now is 1000 ohms. And now using equation 2, that is now our equation 2, derived from this ratio and proportion, RB2 transposition 1.17 RB1 equation 2. Now we have this RB2 1.17 RB1 RB2, and then simplifying, since we know the value of RB2, got RB1 854.7 ohms or 850, my available resistor. So we know that this is 850, 1000, 100, 220. Let us now go to the next circuit diagram. So we got now the values of all the resistors here. This is now a constant voltage source. And then we're going to connect another LED in series in the collector side, in series with D1. This is the blue LED, as we have seen in our toy module, once we slide the jumper. The problem with this is this. So add blue LED to the circuit, which is now the D3. When you're using figure 2, still okay. Using KBL, BCC minus voltage of T1, BCE, BRE. When you're going to compute for BCE, Since we're using transistor in active mode, BCC, BRE, BC1, BRE, BCE is BCC minus BD1, BRE, 5 volts, supply, 1.8, that is LED rating, and then 2 volts given. The BCE is 1.2 volts, in the case that we are still using one LED. While in the case of using another LED in series with this is, we're going to use this figure, in series, what happened is using the KBL, BCC, BD1, BD3, BCE, BRE, BCE, BRE, and now we're getting a voltage across collector emitter of negative 2 volts, making the transistor to operate in saturation mode. That's why we're getting dimmer LED lights once we are using a constant voltage source and putting another LED into the collector side. So to modify the circuit, we're now going to use this, a constant current source. So instead of using a resistor here, we're going to use two zener diode, 1N4148, D4, D5. And now we're going to compute now this RB, R1, no, RB and RE only, because R1 is the power on LED. So that is zener diode 1N4148. And then using figure 4, here, now we got here the given. The forward voltage of the zener diode is 1 volt in 10 milliamps forward current. So when the forward voltage is 1 volt, the forward current is 10 milliamps. The two diode, each 1 volt each forward voltage. We're going to solve for RE and RB1. Here, since we know the voltage, forward voltage of the rating of the zener is 1 volt plus another one, voltage at the base, we're going to compute voltage at the base, which is equal to the sum of the two voltages of the zener diode, is equal to the sum of the voltages of the zener diode. 1 plus 1 equals 2 volts, forward voltage of the zener diode. And also, the voltage at the base equal to the voltage of the two zener diode is equal to the voltage of the base emitter plus voltage at RE. Transposition, voltage base, transposition, substitution, we got the voltage at RE now of 1.3 volts. So we know the voltage here, 1.3 volts. Using Ohm's law, 1.3 volts and 0.02 ampere. Since we're using the same load current, which is 0.02 ampere to turn on the LED. Now we are getting 65 ohms, but I use 100 ohms, my available resistor. And now let us see this. Since we know the value of the RE, we're now using this KBL across BCC, RB, and D5, D4. Using KBL here to compute for RB, BCC minus BRE minus the 2 zener is equal to 0. We now having this BR, that is BRB, not BR1. BCC minus B transposition, substitution, 3 volts. Voltage drop across RB, 3 volts. And now using Ohm's law, 3 divided by 0.01 ampere. Current at RB1, why is it 0.01 ampere? That is the okay, 0.01 ampere. That is the forward current of the zener diode. 3 volts divided by 0.01 ampere. We got 330 ohms available. And now This is now our circuit diagram and the layout. And that is how, by using this zener diode instead of the resistor, we're now using a constant current source. Okay, you can now put your toy module, because of the constant current source, we're getting a nice LED lights using a zener that serves as a regulator, and a constant voltage source is not applicable. Using this is good constant current source. So thank you for watching. Bye bye.